the recording right now. So anybody have any questions about these announcements while we're at it? Okay, hearing none, I'm going to start with a little bit of stuff, and then we'll do the polling, and then we'll get back to some more stuff. But I want to change the sharing here to the old iPad. Okay, so what do I have to tell you? This is about the metal stuff at the end of chapter 19, which it's really important stuff. They're really very, very valuable reactions, as you'll see in some of the examples I give today. But it's kind of a little bit tricky to keep things straight. So this is some preliminary what's going on here with these metals. So if I have, I'll make it this methoxy aromatic. Okay. Anytime you see that guy, you want to be thinking oxidative addition. Okay, you want to be thinking, now I know a metal like palladium or nickel, or now we know even magnesium, can insert in that carbon halide bond. It's not SN2, it's not SN1. It's magical transition metal chemistry. But when you see that, you want to think, aha, if there's a zero valent metal around, it's going to insert there. So that's a big hint telling you what kind of reagents you would need, and note the plural. Oof. To make this molecule. Okay, so I am going from this aryl halide to this coupled, basically it's a biphenyl. It's pretty obvious that I am adding that piece. Now, don't fall into the trap of thinking, I mean, it makes sense to fall into this trap, but don't fall there, okay? I know this should be an electrophile, and gee whiz, it makes perfect sense to me that if I just add this nucleophile, I know this is a nucleophile, I've learned my Grignard chemistry, that this should be able to do this and this, and remember, it just doesn't work. It doesn't work. Grignards don't do this. Grignards don't couple. So what do you need to use? So this is an example where the Suzuki coupling is ideal. So remember, you're thinking oxidative addition. That means you need something like palladium 0. You need a palladium catalyst. And then what is your piece that reacts once you have done that oxidative addition? Well, for now and for this course and for this book, that piece would be a boronate ester, would be crazy, crazy, something that you've seen before, only in the context of boron. So this is an example of the Suzuki. This is what I'd want to do. Add a palladium 0 catalyst. You can put catalyst in there. And wherever you want this yellow bond to form, that's where you're going to put your boron. So let me ask you, and you guys are going to have to just unmute yourselves and stop me and ask questions whenever you have them. Just scream them out, because I'm not, I'm writing on the iPad. I'm not looking at chat or seeing. Yeah.
What is the boron atom called again?
It's called, and don't worry about it, but it's called a boronate ester. But thanks for asking, because I'm about to ask you a question about those boronate esters. Because Karty doesn't talk about this, but it's a good opportunity for some review. Let's say I want to do a Suzuki, and I want to couple this with we'll just call it that. Okay, so now you know it's a Suzuki. Whenever you see this boron piece hanging off, you're thinking Suzuki, you're thinking palladium 0 catalyst. I'll be more specific this time. I'll put palladium triphenylphosphine. There's 4 of those around your palladium. That's a palladium 0. And we'll just say, you know, that's a catalyst. My question for you is, I wonder how we make these boronate esters anyhow. So what is the other reaction you guys know that boron does? What does boron add to in your previous life, your previous organic chemistry life? Two 301, chapter 11. Clearly a hint is necessary. How do I make this? I know what's going on. Everybody has forgotten to unmute their microphones. I'll unmute everyone.
Hydroboration.
Yay! Thank you. Okay, so this is in fact exactly how that boronate ester would be made. Remember that you can do hydroboration with alkynes as well, and it's going to be anti-Markovnikov. And now you know sometimes these boronates are used for something else besides just cleaving them off with, you know, hydrogen peroxide to make the alcohol. So there's the Suzuki. Questions about the Suzuki? Sarah could gladly talk to you in PAL about the Suzuki. She's quite familiar with it. And other coupling reactions, there's lots of them. All right, next one we're going to talk about. Sarah, were you getting ready to say something?
I was just going to say they're really fun to do, and it's a lot easier than it seems on paper, too.
Yeah, they're not bad. And they work incredibly well. It's kind of wonderful. Okay, next question is, what's the product of this reaction? Okay, and I'm going to have to stop and restart here because my screen didn't switch out, unfortunately. Okay, so hold on. Okay, what is the product here? I've got, I'm not feeling particularly creative today. I'm going to use the same aryl halide. And now, instead of adding a boronate ester with my palladium catalyst, I am going to add an alkene. It can be really highly functionalized. We'll make this a ketal. Now, how do you recognize this reaction? Well, again, you're going to see that you have an aryl halide. And yes, it's almost always aromatic halides that are used in these reactions. Note that's a key tip-off that it's an sp2 hybridized carbon. So you're not talking about nucleophilic substitution here. So again, I'm going to be doing oxidative addition. And this is where this part of the OChem course is a little tricky because we just don't really hammer the organometallic mechanisms. But basically, what is the miracle chemistry happening here? This is the Heck reaction, where once you get your palladium inserted in there, it's very cool that your alkene, and I'm just going to abbreviate this R, can coordinate to the palladium and then undergo an insertion reaction. So if you had to draw electron movement arrows, you could, where again, it's kind of like a 1-2 shift. Those electrons swing down, attack the coordinated alkene, and this pair of electrons goes out and attaches to the palladium. So basically, you have inserted the alkene. I think I'll make the alkene blue here so that you can see it. CH2, CH, R, and then here's my palladium. And my palladium still has the bromine on it, and there's 2 other ligands on it, blah, blah, blah. Oh, but none of that should be blue. I just wanted to make my olefin blue. Okay, olefin, aka alkene. All right, so it's pretty cool. Your alkene just kind of slotted right in between the carbon-palladium bond. And now what happens, I'm going to redraw this, it's just such a mess. I've just redrawn it so that you can see that the palladium and hydrogen are both cis to one another. They're both on the same side of whatever conformation this is. And it can now undergo this beta hydride elimination, which is not at all unlike E2. It's just that it's intramolecular, and my base is my palladium. And so that gives me my Heck product. So for those of you who actually know what Tinker Toys are, this really is an example of Tinker Toy chemistry. Because I started off with this, plus this, and kind of miraculously, through the intermediacy of this palladium catalyst, I kind of pluck off each of those hydrogens and then stick those 2 atoms together and get my product. And here is my new bond. And note the retention of stereochemistry. It's an amazing reaction and Nobel Prize winning. Richard Heck won the Nobel Prize for this chemistry. Okay, so questions about the Heck reaction. Okay, well then I'm going to scoot ahead to, do I want to do the polling now? I think I'm going to do the polling now. So I'm going to give you about 5 minutes to answer 5 questions. Again, this poll is anonymous, I just want to see how you're doing, and basically get through as many as you can, and then we'll look at the results and discuss them. So here is our poll on metals. Okay, so let's see how we did. It looks like this was a, we have some work cut out for us yet here in this area of chapter 19, but granted, it's kind of crazy. It's a wild change from what we looked at before. Okay, so they're all kind of artificial questions too because of this polling thing. I can only, write out text. So which reaction stitches together two alkenes to make a new alkene? So it is indeed metathesis with the Grubbs catalyst. Not to say that the Wittig doesn't make an alkene, because it most certainly does. Cuprates can put together an alkene with another alkene, but this one is the one that is, metathesis is really, again, Nobel Prize winning chemistry, which we're about to look at in just a second, that puts together two alkenes specifically. Which of the following accurately represents an oxidative addition? Well, we now know that it's all of the above, that whenever we take metal in its zero oxidation state, like for the Grignard magnesium, for this palladium 0, and for zero valent lithium, all of these are oxidative addition. So the answer here is all of the above. All of those would be oxidative addition. What's so special about reductive elimination? Well, Umpalung is not. It is nothing Umpalungy about it. Both of your groups attached to their metal are polarized in the same way. The oxidative addition does the Umpalung, but reductive elimination, not so much. The most special thing about it is that it makes a new carbon-carbon bond, and concurrently, it regenerates the transition metal catalyst. So the two answers here are the ones that would be correct. And for the trick question number 4, the product of the reaction of one nonene with hydrogen gas is 0 zip nada. Nothing's going to happen without a catalyst. If you have a catalyst in there like palladium or nickel, you would get nonene. So that was capital T trick question. And then finally, since we just went through the Heck reaction, which of these is not a part of the Heck reaction? Well, insertion most definitely is. Addition and elimination is the trick answer. That's chapter 20. Oxidative addition, insertion, and beta hydride elimination are all aspects of the Heck reaction. So you're not required to memorize the reaction, the mechanisms of these metallic processes, but you do want to, sorry, I just now realized I hadn't been sharing the results with you. You do want to have a better idea of what goes with what. I'm certainly not going to make you write out a Heck mechanism, but I can certainly see myself giving you question, which one of these steps represents oxidative addition, for example. So there we go. Questions about any of those poll questions?
Hey, Nancy, for the exam, would there be questions similar to this?
Well, that's a good question, and there will probably be some similar to this just because we're limited to this online stuff. Brian and I are still conferring about how this is all going to work out. I know that, as you know, there's going to be a take-home, and that will be just like our normal take-homes. But the online portion is either going to be multiple choicey stuff through Canvas or multiple choicey stuff through SmartWork. And both of those clearly, unlike this one, can have structures. So does that help answer your question?
Yeah, thank you.
Okay, yeah. Okay, well, let's talk metathesis. Let's talk metathesis. Get rid of this. There's some very cool stuff. I'm going to start with screen sharing here with the iPad, and then we'll move over. Okay. So we're going to look at metathesis, but we're going to do a lot of review in this next series because these are fantastic examples of how much you've learned. So you see this, you think, epoxide, ring opening. Could be under acidic conditions, could be under basic conditions. What I want to ask you is, what reagent or reagents are they adding to go from here to racemic here? And if somebody wants to tell me, that's great, I'll give you 30 seconds, then I'll draw it in. Hearing none, I think you guys would recognize, I hope that you guys would recognize that adding this as my nucleophile is going to attack that and give me the trans addition across the epoxide. Could be acid catalyzed, could be base catalyzed. This is actually a synthesis from a pharmaceutical company called AstraZeneca, which is a very big pharmaceutical company. They used as their acid a Lewis acid, boron trifluoride etherate, okay? There's our boron again, it's just a Lewis pair acceptor, electron pair acceptor, good acid. So I get my racemic ether alcohol, and then I take that and, oh, actually this isn't AstraZeneca, this is a different company. This is to be making glycopivir, read my own writing, hepatitis protease inhibitor. Okay, so I'm going to look at this and I'm going to ask you if you've looked at mini lectures for chapter 20, because what I want you to tell me is the product of this reaction. And if you've looked at the mini lecture for chapter 20, what you will do is say, nucleophile here, electrophile here, and big time up to make the tetrahedral intermediate, back down again, and kicking out the good leaving group, the acetate here. So this is chapter 20 chemistry. And I'm still making racemic products here. So this is called an acetylation or an acylation with acetic anhydride. Chapter 20, the mechanism is the same throughout. Okay, so pharmaceutical companies like AstraZeneca cannot sell racemic products. They have to sell enantiomerically pure pharmaceuticals. And so they have to get rid of the racemic bit and come up with an enantiomerically pure compound. And they do that by enzymes. Cool stuff, beyond the scope of this class. I expect that if you take the synthesis class next spring, you will learn all about it. All right. This is, let me just forge onward. This is all going to come together. Trust me. All right, so another part of their synthesis, and just a little heads up, pharmaceutical companies, medicinal chemists, all of the above, like to use fluorine in their molecules because it's a good way to mess with metabolism, mess with the way a drug operates in the body, because a fluorine is about the same size as a hydrogen, but it doesn't act like a hydrogen, can't be removed like a hydrogen. And so this is a good way to design inhibitors, for example. So this is a nice small molecule. I am going to ask you to explain in your head what is going on. This is going to use a reagent we haven't seen before. So I have this halide, and I'm adding a zero valent metal, indium. And the reason why we're using indium is because it can be, this reaction can be carried out in water, which is a very obviously a green solvent. So the product of this reaction is that. So what do you think's going on here? Explícame.
The nucleophilic carbon off of the bromine goes and attacks the electrophile.
Exactly. Yep, excellent. So two things to think about. Number one, patterns, patterns, patterns. Could be an organolithium. Could be a Grignard. Could be indium, for crying out loud. All of these are making this carbon have a polar bond that makes it a carbon nucleophile. So that's item number one. Item number two is, you should be thinking, why here and not at the ester? And as we'll see, or have reinforced in chapter 20, aldehydes really are much more reactive than esters because the oxygen is pumping electron density into the ester, making it less electrophilic. So we get to that particular molecule, and then I'm going to ask you, how do I go from here to here? What reagents would I use? You're taking an exam, I give you this on the exam, what are you going to put down? You have no idea. Take a wild guess. Well, I hope you would wildly guess that this is the oxidation state of 0. This is the oxidation state of +2, so I'm going to add an oxidant. The particular oxidant they use, I don't know. What one would we use? We could use chromium trioxide, we could use PCC, we could use KMnO4. Pick an oxidant, any oxidant. All right, now here's the one I'm going to let you work on as a take-home assignment, not for points, just for practice. I've made that molecule, so I've gotten to this point. So remember, we're making this protease inhibitor. This is what we've got, and we're going to add this. Oop. I don't have any of the other reagents written down, but you can see nucleophile, nucleophile, oops, not there, electrophile, electrophile. The end product that we are making yeah, is that guy. Good practice for you at home is to come up with the mechanism for this transformation. It's good old-fashioned chapter 17 or 18? 18 chemistry with a little bit of chapter 20 thrown in. So I would encourage you to do that. Then, just out of fun curiosity, how would you go from there to here? Because that's what they did. Oops, wrong. You should have lots of questions about this, by the way, like how come those fluorines are hanging on throughout this whole synthesis? Well, bromines are a lot more active than fluorines are. Fluorines are really quite inert. How do I go from the hydroxyl group to the chloride? Well, clearly, I could use HCl, right? I hope everybody's shaking their head no, because that would be a really bad choice because of the double bond. Synthetic trap time, you would need to use, not that, honest to Pete, must be Monday, thionyl-chloride. Okay, so tons of chemistry that you know and or can figure out. Now, we go to the rest of the synthesis, which is here. Okay. No, don't show all the answers. Jeez, that's no good. Okay, so what I think you can see here, my little pointer. Okay, this is the piece we were just making. Okay, and don't worry about where this came from or how it got on there. We can figure it out, but we're not going to. Okay, they're going to put these two pieces together, 5 and 6. This is a little alarming. There's an awful lot of stuff on here. You can tell me what the product of this reaction is. We just need to take a deep breath and think it through. So we have alkenes. That's not doing much. We got esters. We got ethers. Ethers don't do diddly squat. But we have a nucleophile here. And we have a potential electrophile here. So this is another example of chapter 20 chemistry. And we learned very simplified basic chapter 20 chemistry. But basically, this is going to be a coupling reaction where I'm going to take an amine right here, and it is going to react with this carboxylic acid, we're going to add some other reagents to make this work, to make this amide. Okay, so like I said, we learn basic chemistry like acids, base, and things like that. There are more fancy schmancy reagents that you don't need to worry about. But basically these make your carboxylic acid activated so that it can react with this amine to make this amide right here. Okay, so that's chapter 20 chemistry. Basically we're going up, down, and out, and making this new amide. Why? Okay, where are we going? Please focus right here. Why are we going to all this trouble to have these two alkenes handy dandy right next to each other? Anybody want to venture a guess as to what organometallic reaction is going to take place next?
Metathesis.
Yay! Good job. Excellent. And these ring closing metatheses work very, very, very much better than acyclic, non-ring closing metatheses because they're held in the right position. There's not a regiochemistry orientation issue, et cetera, et cetera. So yes, they are in fact, I don't know if you can see this, doing the ring closing right across there to make a, let's see, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 membered ring. This is a huge big deal. That's very tough to do without a reaction like metathesis. Other things to note about metathesis. I have oxygen, carbon, carbon, carbon. I have 2 carbons next to my fluorine. Well, what you can see is I have lost 2 carbons in this ring closing metathesis reaction. In other words, it's like we chop off the end of this alkene, we chop off the end of this alkene, and then we stick them together. So that is a metathesis reaction that's carried out with Grubb's catalyst. Okay, here's the rest of the chemistry. What do they do next? Oh my God, what a mess. What a mess. But what I want to show you is, again, it's chapter 20 chemistry. And why is chapter 20 chemistry such a big deal? Because a lot of these biologically active molecules are amides, are peptides, all right? So a polyamide is a peptide. So you want to know how to do these syntheses. And this just puts together this amine with this carboxylic acid. So super important chemistry in chapter 20, but also coupled, no pun intended, with some pretty amazing organometallic chemistry as well. All right, I will pause now and unmute people just in time to hear somebody coughing. I hope it's just a tickle in your throat. Questions. I have lots more problems to go through, trust me, but questions.
For chapter 20, how do we like know which one for sure gets kicked out, or does it happen in equilibrium?
Well, it's definitely an equilibrium reaction. And the good news is for this class, primarily you're not going to have to face those choices. The examples I just went through were a lot more complicated, obviously, because there's so many other things that can happen. Typically, it's, oh, well, not typically, always in OChem, it's a combination of sterics and electronics, right? So maybe if you have two esters or two, like we're doing a transesterification, and there's one ester on the molecule that is a tert butyl ester, and there's one ester in the molecule that's a methyl ester. The methyl ester is the one that's going to react because that tert butyl group on the other ester really protects it from being attacked. Does that kind of answer your question?
Yeah, and then can we not do that in the presence of hydrogen then, because of the negative oxygen just getting protonated?
Yeah, so these examples I just went through are really quite a bit different from the ones that you'll see in the textbook. In the textbook, what I will emphasize as well is that, you know, you cannot make an amide from a carboxylic acid, because the only thing that will happen is proton transfer. But let me share my screen quickly again. These, well, I don't know if you can see my cursor, but these reagents, they are basically reacting first with the carboxylic acid to make it active and getting rid of that proton on the carboxylic acid, which otherwise would just be deprotonated by the amine. So, does that answer your question?
Think so.
Okay. Okay, other questions? Okay, questions about the Heck reaction? Questions about metathesis? Cuprates? Okay, let me give you one more example of a metathesis reaction. A metathesis reaction that doesn't really work well, and it was a bear and a half to get it to work as well as it does, just to illustrate why you have to be kind of picky sometimes in synthesis. Okay, so here is one more example for you that takes advantage of reviewing what you already know. Okay, this happens to be the AstraZeneca reaction or sequence I was going to tell you guys about. So you tell me what you need to add to go from the aldehyde to that alcohol. Okay, I'll work on the assumption that everybody I think everybody's unmuted right now, just so you know. Everybody would say, okay, I'm going to go with the tried and true. I'm going to add the Grignard. And that, in fact, is exactly what they did. They used the magnesium chloride, and this reaction took place in a pretty decent 76% yield. All right, question number 2. How would they go from there, or what would they add? And this is the tricky one, I guess I'd say. Ugh, that's a that's a mess. That's methyl ester. How am I doing this? And that's definitely a tricky one, because if you look at this, I think you would say aldol. But what's fishy about this is that this is your starting material. So if you look at it, it's as if I'm adding these two together somehow, putting together two alkenes. Should be screaming metathesis. So that is in fact what they did. They used metathesis reaction to get this, and this is an example of not a ring closing. I think you can imagine that you'd have all kinds of byproducts with this metathesis reaction. So you would use the Grubbs catalyst, which is a ruthenium catalyst. And what you can imagine is that this guy could stick together with itself. This guy could stick together with itself. I could have an E double bond, I could have a Z double bond, and so on and so forth. So metathesis has its issues, and you know, it's not always a great choice, but sometimes it's a phenomenal choice. And in fact, it's a phenomenal choice for making an awful lot of polymers. All right, so I am going to stop with the metal reactions and change my focus to synthesis from chapter 19, unless anybody wants to throw out a topic that you're really confused about and really want me to answer questions on. I'm pretty sure that anybody would happily say, oh no, go ahead and do synthesis. We're always happy to have you go through synthesis. So let's do that. We'll take about 10 minutes to do some syntheses problems. And I want to start, these are all problems from Karty. I want to point out that he does a phenomenal job with helping you learn how to recognize synthetic pathways, I guess I'd say. So here is a target. And here is a target. Without any other information, what kind of chemistry do you think you should use for making these compounds? So this is 19.43, and the purpose of 19.43 is to help you recognize the relative positioning. So even though this is not an aldol product, it makes sense for you to consider an aldol to make this, because your functional groups are 3 atoms away from one another. So it makes sense that perhaps I could get to that target from this aldol, or maybe this aldol. And in either case, I would have a further disconnection here for making the aldol from smaller pieces. Ultimately, synthesis is about trying to make a bigger, more valuable read more expensive, read more value to the stockholders for this particular company, trying to make a value-added product from smaller pieces. So even though I could certainly think about making that target from electrophilic addition across a double bond, that's not making a value-added product so much. It's not adding carbons. It's not making a bigger molecule. It's not making a more complex molecule. All right, so when I see the 1,3 positioning, I definitely want to think aldol and put that in the back of my head. How about this guy? Okay, so this guy, 1, 2, 3, 4, 5. if I'm thinking relative positioning, I should be thinking, maybe that would be a Michael reaction. Maybe if I think about this Michael reaction, I would get two pretty substantial pieces put together right there, and then the subsequent step, I could reduce the ketone that would form right here, reduce it with sodium borohydride or lithium aluminum hydride. So, very important key. Oh, that's not going to work. Oh, that doesn't really look like a key either. But think about relative positions. Of your functional groups, because that will give you a big hint. All right. Item number 1. Item number 2, something we didn't talk about before, and I feel as though we need to talk. We need to talk. The biochemistry that's presented at the back of chapter 18 is very important because it's happening in you. It's absolutely imperative if you're going to be taking biochemistry. If you're in any pre-health field, you need to know this. But it's also good for all of us because we review how to draw A, cyclohexanes, chair conformations, and B, everybody's favorite, Fisher projections. So here is a handy dandy molecule of glucose. And one thing you need to be able to do is A, recognize the anomeric carbon, and B, draw out the ring opened form of this carbohydrate. In other words, the ring closed hemiacetal is in equilibrium with the alcohol and aldehyde. It's just that the ring closed form is more stable in this example because it's a 6-membered ring. So how do I draw this ring open form? Well, the easiest way is to identify the anomeric carbon. Remember, that's the carbon that has 2 carbon-oxygen bonds, and it's that one right there. And then recognize that I could use my favorite, most reliable disconnection ever, the alcohol disconnection, to put that alcohol back over here where it belongs. And here's my aldehyde. I won't move anything else. There is the ring open form of my, this is, I do believe, this is glucose. So, turns out, like I said, because it's a 6-membered ring, the ring closed form, otherwise hemiacetals are not stable, but the ring open form is less stable than the ring closed form. And what is important to point out here is that now that you know that there's an aldehyde in here, it can do any reaction that any normal aldehyde would do. All right, it can make imines, it can be reduced, and so on and so forth. So keep that in mind. Now, just to add fuel to the fire here in the review section, make sure that you can convince yourself that this Fisher projection is actually an accurate representative. And it's not trivial. But these all represent the same thing. And again, if you're going to be taking biochemistry or doing any research in biochemistry, you will need to be able to translate these, keeping in mind that these Fisher projections look like that. The horizontals are coming out towards you, the verticals pointing away from you. So if I am zooming around up here in my Superman cape and looking down on the molecule like this, I can see the OH is on my right. And that the vertical pieces are pointing away from me. So I know that that is the correct configuration at the top bar of my Fisher projection. Okay. Fun stuff. All right. I think we have time to do one quick example of protecting groups, and then I will set you free. How do you go from here to here? And I'm not going to worry about the stereochemistry. Actually, let's do this. Let's make it here. Very interesting. Okay, everything about this says do this. No, I don't like that one. Everything about this says do this. But you can't do that because of that. So your synthesis would have to include a protection step. So I'll let you fiddle with that. That's a great problem for you to think about. I think maybe we'll start Wednesday's class with that before we break out into our breakout rooms and you do your in-class homework. All right, any last questions? All right then, go on to your next fun activity and we will see you on Wednesday.